So this week is the last lab test. Anybody have any questions related to that before I go on to new stuff? Okay. The main topics? Well, it's, it's all the labs now. So the new stuff is... the new stuff that's on it since the last lab, what would that be? The thing where, I think the Newton's third law thing, where the contact forces are the same on the two bodies, but the accelerations that's caused by that contact force is bigger for the small body, smaller for the big body. And then the second thing is Newton's first law. The thing that says if there's no net force, the object keeps moving in a straight line with a constant speed. And then all the old stuff, too. Yes. So the first one was a combination of Newton's second law and Newton's third law. And it worked like this. When two things are two things collide or they're in contact, they apply the same forces to each other. Well, opposite directions, but the same magnitude of force. That's because of Newton's third law. But they don't produce the same acceleration in the two bodies. The smaller body accelerates more due to that contact force than the bigger body. And the best example of that is like a big truck in a collision with a little car. You know, the reason you don't want to be in the car when that happens is because the car accelerates a lot. The truck doesn't accelerate very much. And then the second thing, the second new thing is Newton's first law. And that says if there's no net force on an object, then the object keeps moving in a straight line with a constant speed. That is actually required by Newton's second law, because Newton's second law says, F net is equal to mass times acceleration. So if F net is 0, acceleration is 0. And this is something you should remember. This is like useful for cocktail parties and whatnot. So I don't think this is probably actually in thesauruses, thesauri, but it should be. So these mean the same thing. 0 acceleration and constant velocity. Okay? Those two mean exactly the same thing. If you have 0 acceleration, you have constant velocity. If you don't have 0 acceleration, you don't have constant velocity. It's different ways of wording the same thing. So like when you're at a cocktail party and someone's talking about 0 acceleration and you're like, I don't want to sound like I'm just like copying them. You can say constant velocity. It means the same thing, but it sounds different.
The net force follows the total acceleration.
Right. So yeah, Newton's second law says F net is equal to mass times acceleration. So if F net is 0, the acceleration has to be 0. Or in other words, velocity has to be constant. Or if velocity is constant, that means acceleration is 0, and that means the net force has to be equal to 0. So what's happening so think about this for a second. Say you have this big, heavy, those old trunks. We used to have one in our basement. They have these funny latches like that, little handles on the sides. They weigh like 100 pounds. Okay, so say you're pushing this across the floor. This is you. You have a really sharp butt. That's how heavy it is. Okay, so what's going on here? So let's say you're pushing this thing across the floor in a straight line with a constant speed. Okay, well, if you're pushing it in a straight line with a constant speed, that means constant velocity, which means acceleration is equal to 0, which means F net is equal to 0. So how can that be? Because if you drew a free body diagram of this thing, there are all these forces. There's a big weight force. There's a normal force. There's a friction force resisting the motion. And there's a force R being applied by U. So how can it be with all these forces acting that the acceleration is equal to 0? It seems sort of like a paradox, you know? But that's the deal, is Newton's second law, Newton's first law don't say that if there's no acceleration, there are no forces acting. It just says if you add up all the forces, they add up to 0. So even though there are 4 different forces acting, the 2 vertical forces offset each other, and the 2 horizontal forces offset each other. That is his first or his second. So remember, I said in lab that the first law is actually contained in the second law, which is why in class we only talked about the second law. Yep. Yes?
So if it was constant speed, but it's turning, you would have an A perpendicular.
Right.
But still no total acceleration.
No, you would still. So if it's turning, you have an A perpendicular. That's exactly right. Then the total acceleration is equal to that A perpendicular. And then F net is in the same direction as that total acceleration. So then you do have to have an F net. So Newton's first law says if something's moving in a straight line with a constant speed, F net is equal to 0. What it doesn't say is if something's moving with a constant speed, F net is required to be equal to 0. Because if it's turning, F net has to be something. Any other questions right now? Yes?
So in this example, the friction is equal to the force being applied by a person?
Yes, that's right. The magnitudes are the same. Yep. Any other questions? All right, so we're talking about conservation laws right now. The first one we talked about, and we're done with it now, is conservation of linear momentum. And when was that useful?
You're catching a ball standing on a skateboard.
That was one very specific example. Collisions and explosions, yeah. And we're done with that. And now we're moving on to the second one, which is conservation of energy. And in deriving conservation of energy and introducing it, I'm going to first talk about what's called the work energy principle. So really that, so work energy principle is what I'm going to introduce first, and it's going to simplify in certain cases to conservation of energy. Who knows whether you spell this kind of principle P-L-E or P-A-L? There's two different kinds of principles. Yep, L-E. And you know how you remember that? Yeah, because your principal is your pal, exactly. So if you're talking about like the number one, that the main item in a category, that's like the principal employee at your school or whatever, that's PAL, because the principal of your school is your pal. If you're talking about a bullet point, that's PLE. Now you know something. And conservation of energy is going to be useful in cases where, so we're going to use this for kinetics. And the cases of kinetics where this is going to be useful are where we're trying to relate an object's position to its speed in some way. So I'll try to bring that up as we, as examples start coming up. So the thing that gets a little tricky with conservation of energy is now this is maybe the first time that we're learning about a method where we have another way of approaching these problems. Like we have other ways of doing kinetics problems. And so we have to be able to differentiate when you want to use Newton's laws for kinetics and when you want to use conservation of energy. And the key is conservation of energy is going to be useful whenever the problem is relating in some way, saying what's the person's speed going to be at the bottom of this hill, or at what position is the person going to come to rest or something. In those cases where we're relating a speed to a position, we're going to use conservation of energy. Okay, so conservation of energy. And we're going to come to this from the work energy principle. So this is a second approach to kinetics problems. It turns out that any problem that you can do using conservation of energy, you could also do using Newton's laws, and vice versa. But I don't know about every problem, but all the problems we're going to deal with are going to be much easier with one approach versus the other one. And so we want to be clear about when it's a good idea to think about, conservation of energy and when it's a good idea to use Newton's laws. This is more useful than Newton's laws. When we're relating position to speed. So before I start going into equations, let me just say something about energy. So the SI units for energy any kind of energy, and we'll see that there are a lot of different kinds of energy, are kilograms meters squared per second squared. And since this is a really common thing that comes up in physics, it's given its own name, the joule, and it's abbreviated with a capital J. So 1 kilogram meter squared per second squared is equal to 1 joule. And the way we're going to use energy is with the work energy principle. And the work energy principle says W total, I'll talk about what all these mean in a second, W total is equal to the change in kinetic energy. Where W total is the work done by all forces on the chosen object and KE is the kinetic energy. So before we can go on, we have to come up with mathematical definitions for these things. So we have to define work and kinetic energy. So first, kinetic energy. That's the one that's a little simpler to define. An object's kinetic energy at a chosen instant is 1/2, so KE is equal to 1/2 times its mass times its speed squared. This V is the speed. And if instead of the speed you have the components of the velocity, you can also write this as 1/2 times the mass times the square of the x component of velocity plus the square of the y component of velocity. So a train has a lot of kinetic energy because it has a big mass and it's moving really fast. A snail has very little kinetic energy. Because it has a small mass. And it's moving slowly. We've actually talked about another quantity, well, just last class, I think, that measured sort of similar things. So do you remember what the quantity was last class, I guess before the test, where we said something large moving fast has a high amount of this quantity? So it measures sort of similar stuff to momentum. Remember, momentum, we called it lowercase p, and it was equal to the object's mass times its velocity vector. So a train has a lot of kinetic energy, and it also has a lot of momentum. A snail has very little kinetic energy, and it also has very little momentum. The biggest difference between those two, well, one is the squared. But the main thing to notice is momentum has direction. It's a vector quantity. Momentum is a vector quantity, so it has directional information. Kinetic energy like all energy, is a scalar value. So it's directionless. So when you use momentum in equations, it matters whether the thing is moving, north or south or whatever. When you're using kinetic energy in an equation, it doesn't matter what direction it's moving. Any questions yet about kinetic energy? Okay, so the next thing we have to define, we're working our way up to the work energy principle. We're working our way up to this. We've talked about what kinetic energy is, but we haven't talked about what work is yet. So work. Work is energy added to an object by the application of a force. That's not the only way you can add energy to an object. You can add energy to an object by subjecting it to a temperature gradient. If you put an object on something hot, there's a temperature gradient. Energy goes into the cooler object, And that type of energy change is called heat. But this one is, we're only talking about the energy added to an object by applying forces with this. And for us, we can calculate the work done sorry, let me change this. You can calculate the work done. Let me change it one more time. Can calculate the work done by a force as an object moves if the force remains constant. So let's say that an object so if an object's displacement is the vector d, and the force is F, then first, if F and D are in the same direction, then work is positive, and energy is added to the object by that force. On the other hand, if F and D are in opposite directions, the work is negative. And energy is removed from the object. Okay, so let's think of a couple examples before we put numbers to it. So first, let's say that a cart is moving this direction, and a force F is applied in the same direction as the velocity vector. Then the displacement vector, you know, you can think of like, let's see. You can think of the object as starting here. There's the start point. There's the ending point. So are the force and the displacement vector in the same direction or opposite directions in this case? Yep. So F and D are in the same direction. which means energy is added to the object. Okay. Does it make sense intuitively that, so if the object's moving to the right, and you're also applying a force to the right, what this is saying is that basically, the mass of this thing isn't going to change. So the only thing that can change is the speed. Does it make sense that if you apply a force in the same direction that it's moving, that force is going to contribute to increasing the speed? That does, right? So that's what it's saying. So the object speeds up. On the other hand, let's think about like a friction force. So here's the object. It's still moving in the same direction. We'll say that's the starting point. Its velocity is this way. We know that its friction force then has to be this way. So are F, this friction force, and the displacement in the same direction or opposite directions? Yep, so the friction force and the displacement are in opposite directions.
So in that example, you just pushed it, let go. There's no.
That's right. Yeah, so there were forces applied before or whatever, but shoved it and then let it go.
Okay.
And so, although actually, when we're doing these analyses, we're thinking of the forces one by one. So it could actually, it would be also reasonable to think of this as like someone's still pushing on it, but all we're analyzing right now is what the friction force is doing. That's not a free body diagram in this
If
case.
somebody was still pushing on it, then it could be the top if they're overcoming the friction.
So what you would do is calculate the work of those. Those are two separate forces, and you'd calculate the work done by each of those two forces separately, and then add them up to get the total work. Okay, so these are in opposite directions, and that means that energy is removed from the object. So again, the only way that kinetic energy can change for that thing is for it to speed up or slow down. If energy is removed, it means that that object is slowing down. So does this make sense intuitively, that that friction force is going to contribute to this slowing down? Yeah, that's all friction does. That would be cool if you could find friction that sped things up, but good luck with that. So in this case, the object slows down. And in fact, they don't have to be, that force and the displacement vector don't have to be in the exact same direction or the exact opposite direction. As long as they're within, like if you put them tail to tail, if they're within 90 degrees of each other, then energy increases. And if they're farther than 90 degrees apart, then energy decreases. And so here's how the math works. So there are two ways that we have for calculating the work done by a force. The first is if you know the components of the force and you know the components of the displacement, the work is equal to, this kind of multiplication is called the dot product. So it's the force dotted with the displacement vector. And the way you calculate that is it's the x components multiplied together plus the y components multiplied together. Or equivalently, if you put the two vectors tail to tail, the work is equal to the magnitude of the force, just the total length of that force vector, times the total length of the displacement vector, times the cosine of the angle between them. Okay, so for example, let's say we have a force vector that's equal to 10 newtons and a displacement vector that's equal to, let's say, 20 meters. If I draw these two vectors, the displacement vector looks like this. The force vector looks like this. Are those two vectors more, like which one is more true? Are these two in the same direction or the opposite direction? Same, and so we expect the work to come out to be a positive number when we do that calculation. Same direction. And so to do this calculation, the work is equal to the x components multiplied together plus the y components multiplied together equals 20, and the units are joules. And since it's positive, we know that energy is added. Okay, so here's another example. Let's say that we have a displacement of 5 meters. And a force vector of 30 newtons. And when you put these two tail to tail, let's say that this angle is 110 degrees. are those closer to being in the same direction or the opposite direction? And so when we do this calculation, we expect the work to come out to be negative. So work is equal to 30 times 5 times the cosine of 110 degrees, which is 150 times negative 0.342. Can someone multiply that? I can't do that in my head. Negative 51.3 joules. So energy is removed from the object by that force. Okay. So what happens when, I said that the cutoff is 90 degrees. If those two vectors, the force vector and the displacement vector, are less than 90 degrees apart, we get a positive work. We add energy. If they're more than 90 degrees apart, you get a negative work. You remove energy. What happens when they're exactly 90 degrees apart? So this is sort of a key idea. What happens when the force vector and the displacement are exactly 90 degrees apart? So like, for example, let's say we have a displacement this way of 20 meters, and we have a force this way of 120 newtons, and they're 90 degrees apart. Yeah, well, what happens, so the work is equal to 120 times 20 times the cosine of 90 degrees. And what's the cosine of 90 degrees? 0. So this comes out to be 0. And no energy is added or removed. Okay, so we're going to come back to that. In almost every problem that we're going to do, there are going to be forces applied to the object that are 90 degrees from the direction of its motion. So if the force is always perpendicular to the direction of motion, that force does 0 work. Okay. So now let's say that there is a guy standing on an elevator. Let's say that he has a mass of 50 kilograms, and it's accelerating upwards at 4 meters per second squared. If you go through Newton's laws, you can figure out that. So Newton's second law would tell you that a free body diagram is like this. There's a weight force acting down of 490.5. And a normal force pushing up of I think that would be 690.5. We've done calculations like this, but for now, we can just start with these forces being known. And the questions are, first, what's the work done by the weight as the elevator rises 10 meters. Second, what's the work done by the normal force as the elevator rises 10 meters? And then last, what's the total work done on the man as the elevator rises 10 meters? Okay, so part A. So if the man, starts there, ends up there, this distance is 10 meters. The displacement vector is this. So the displacement vector is in the positive y direction with a magnitude of 10 meters, 0, 10. Any questions about getting that displacement vector? The weight force, it has a magnitude of 490.5. It's down in the negative y direction, so this is 0, negative 490.5. And so the total work done by the weight is, I'm going to use the dot product. So multiply the x components together and add those to what you get when you multiply the y components together. And you get a total value of negative 4,905 joules. Okay, so that says that the weight is taking energy away from the man. Does that make sense? Can you? So what's happening is, the weight is acting in the opposite direction of the motion. And so the weight is fighting to try to prevent that motion. So the weight is slowing him down. It's trying to cause an acceleration that's in the opposite direction of the velocity. So now let's see what happens with the normal force. So the normal force is equal to, the normal force is 690.5 acting in the positive y direction. So that's 0, positive 690.5. The displacement vector is still the same. That's 0, 10. And so the work done by the normal force is 0 times 0. That's the x components multiplied together, plus 690.5 times 10. And so the work done by the normal force is equal to positive 6,905 joules. Okay, so that normal force is acting in the same direction that he's moving, and so the normal force is adding energy. And then the last one, we want the total work. The total work is just the sum of the work done by all of the individual forces. So the work done by the weight plus the work done by the normal. So that's negative 4905 plus 6905 is equal to positive 2,000 joules. Okay, so what this says is overall the forces added energy to the guy Okay, so does that make sense with what's happening in the problem? Well, it's going up, so we know the velocity is positive. We know the velocity is up. We're given that the acceleration is up. So the velocity and the acceleration are in the same direction, which means he speeds up. Okay? So thinking about it in terms of Newton's laws and the way we've been thinking about it up until now says he speeds up. Thinking about it in terms of work tells us energy is added, so he speeds up. It's a different way of thinking about the same stuff. Anybody have any questions about that? I'm always a little unsure about how to introduce this stuff for this reason. All of this stuff that I've said pretty much so far is going to be kind of irrelevant for doing the problems, you know, but it's important for trying to understand how this all works. So these kind of calculations you're not going to do in problems, but they're all sort of underlying to how the way that we will do calculations, the way it's done. Okay, so now we have to talk about conservative versus non-conservative forces. So if a force depends on, at most, the object's position, it's a conservative force. One way to think about that is if finding out the object's position is enough for you to know the magnitude of the force applied or the force vector that's applied, then that force has to be conservative. So let's think about some conservative and non-conservative forces. Okay, so say that you know the mass of this pen. If I tell you its position, is that enough for you to know the force vector applied by gravity? So say I tell you the pen is right over the table, 2 meters off the ground. Is that enough to know the weight force applied to this? Yeah, and in fact, that's even more information than we need. The way we treat weight is no matter where it is, the weight force is the same. But if I tell you that it's a foot off the table, that's enough to specify the weight force. If I tell you it's 3 feet off the table, that's enough to specify the weight force. So that says that the weight has to be a conservative force. Okay? Any questions about that? So let's think about one that's not conservative. If I tell you that the stapler is sitting at this location on the table, is that enough information to specify the friction force vector? No, because it could be at that position moving this way, and we know the friction force then would have to be that way. Or it could be moving this way, and we know the friction force has to be that way. So its location doesn't give enough information for us to know what that force vector is. Okay? The normal force is another example of one that's not conservative. The location isn't enough information. Because say I tell you that this is the location, is that enough to know what the normal force is? No, because right now the normal force is 1 Newton. Okay? 1 Newton pointing up. Now it's in the same location, but I'm pushing down on it with 50 newtons, and now the normal force is 51 newtons. Then the location didn't change. Okay, so normal force and friction are not conservative. The weight force is. Yeah. It's actually going to get even easier than that because there's only two conservative forces that we're going to deal with in this class. But so, for example, weight is conservative. Normal and friction forces are not conservative. So that's sort of how to trying to help you understand the idea of a conservative force. But as far as figuring out in a problem whether a force is conservative or not, to us there's only two conservative forces. Everything else is non-conservative. In this class, only two types of force are conservative. The first is weight, and the second is spring forces. And so the way that works is, say that this object was attached to the wall with a spring, okay? It's like a long spring connecting the wall to this. Because of the way springs work, to figure out the force that that spring is applying to this pin, it would be enough to find out how far from the wall it is. The length of the spring tells you what the force is. So if we're told that the pin's a meter from the wall, based on that we could figure out what the spring force is. If we know it's an inch from the wall, we could figure it out. Okay. Another way of talking about conservative forces is field forces. So if a force is a conservative force, you can represent it as a force field, which is usually a lot more boring than the force fields in like Super Friends and He-Man and stuff. But it just says that, like, the idea of a force field is, well, what happens in a poppy field, you know? Like a poppy field, the idea of a poppy field is no matter where you go, there's a poppy there waiting for you, you know? And the idea, right? You know what a poppy is? You make heroin out of it? The idea of a force field is really like the same thing. It's like no matter where you go, there's a force there waiting for you. So you can think of, so another way to think of the way gravity works is there are force vectors waiting everywhere to be called into action by the object moving to that location. So there's a weight force waiting right here, and when the pin gets there, now this one is off the bench in the game, and it's applying that force to this thing. So anyways, that's what a force field is. So like in The Incredibles or whatever, like somebody who has a superpower to like create force fields or whatever, like, yeah, I have the power to create force fields, a gravitational field. It's not really that exciting though. But here's the reason that conservative forces are really important. So the reason conservative forces are useful, or maybe they are easier to deal with, is they have something called potential energy. And the work done by a conservative force as an object moves from one point to another is given by this relationship. The work is equal to the negative change in potential energy. We only have two types of conservative forces. And so for weight force, the potential energy gravitational is equal to the mass of the object times 9.81 meters per second squared times the object's height. And for spring forces, the potential energy of the object connected to the spring is 1/2 times k times x squared where x is the object's distance from its resting length, from the spring's resting length. And k is called the spring constant. Where a big value of k means the spring is really stiff, hard to stretch. And a small value of k means the spring is flimsy, easy to stretch and easy to compress. Okay, so now that we have talked about potential energy and the relationship between potential energy and the work done by conservative forces, we're going to use potential energy to restate the work energy principle. The work energy principle originally says, way up here, the total work is equal to the change in kinetic energy. Well, now, for any conservative forces, we're going to represent the work done by the conservative forces in terms of the potential energy. So now I'm going to write this as the work of the non-conservative forces is equal to the change in kinetic energy plus the change in potential energy. It's the exact same equation, it's just now we've used the fact that the change in potential energy is equal to the negative of the work done by, yes?
Do you mean conservative?
No, so the total work is done by two types of forces, conservative and non-conservative. The work that's done by conservative forces is dealt with here. So the only stuff that's left is the work done by non-conservative. Those are the hard ones to deal with, okay? But it turns out that in the problems we're going to do, those are going to end up being 0. And here's why. So, in fact, in our problems, the non-conservative forces will always be perpendicular to the velocity at every instant. And I mentioned earlier that because of the way the dot product works, if a force is perpendicular to the direction of motion at every instant, the work done by that force is 0. And so because of this, the non-conservative work is always going to be 0 in our problems. And so when that happens, which will always happen in our problems, it doesn't always happen in general, but in our problems it always will, that gives the equation, for the work energy principle, 0 is equal to the change in kinetic energy plus the change in potential energy. Or another way to write that is the kinetic energy plus the potential energy at instant 1 is equal to the kinetic energy plus the potential energy at instant 2. Okay. So mathematically, this is all we're going to use, but it's, there's more going on than just this equation. So, I don't know. Try to sort of walk the fine line between explaining what's going on and giving you the practical stuff for the problems. This is all that we're going to be using. So next time I'll just do some example problems. That's all.